Hello friends, welcome to iLearn. Today in this lecture of partial differential equations, we are going to study homogeneous wave equations. And in homogeneous wave equations, today we are going to consider semi-infinite string problem with a free end. So friends, in our previous video lecture, we had covered a semi-infinite string problem with a fixed end. Today the difference is that we will be focusing on free end condition. That is, that end will be free to move. Now this problem can also be termed as the Cauchy problem of a semi-infinite string with a free end. Now friends, so in our previous video lecture we had considered this semi-infinite string problem with a fixed end. Now what happened in this problem, we had that in our string it's a one end, that is x equal to 0. This end was fixed, and what we meant by this fixed end was that a displacement at this point was 0. That is, displacement at x equal to 0 was 0 for all times t. So we had the fixed end condition as u at 0 comma t equals 0. So this was the mathematical expression for the fixed end condition. Now in today's video lecture we have a free end. Now what will happen in this semi-infinite string problem with free end is that one end, say x equal to 0, this will be free to move. Now what we mean by free to move is that we will have displacement at this end. That is, when this string will undergo vibrations, even the particles at this end x equal to 0 will be undergoing displacement. So the particles here will be displaced from their mean positions. So in these vibrations, the end at x equal to 0 will also undergo displacement. So this is what we mean by the free end condition, that is, this end is free to move. Now this free end condition is also termed as free moving boundary condition. What happens in this free moving boundary condition is that the boundaries are free to move. So in this case, this boundary x equal to 0 is free to move. And the mathematical expression for the free moving boundary condition is that del u over del x equals 0 at x equals 0. So this we can also write as ux at 0 comma t equals 0 for all times. So the partial derivative of u with respect to x at the point 0 comma t equals 0 for all t's. This is the mathematical expression for the free moving boundary condition. So friends, the mathematical difference between this problem of free end condition and the problem we discussed in our previous video lecture of the fixed end is that in this problem we have the mathematical expression as ux 0 comma t equals 0 for all times t, whereas in the previous video lecture when we discussed the semi-infinite string problem with a fixed end, there the mathematical expression was u at 0 comma t equals 0 for all times t. So this is the difference in terms of mathematical expressions between this problem and the problem of the fixed end which we considered in our previous video lecture. So now let's derive the solution for this semi-infinite string problem with a free end. Now friends, let's see this semi-infinite string problem with a free end in its mathematical form. Now this expression utt minus c square uxx equals 0 for x positive and time t positive represents the wave equation. Now this u at x comma 0 equals fx for x non-negative represents the initial condition for initial displacement. Next, ut at x comma 0 equals gx for x non-negative represents the initial condition for initial velocity. And next we have the free end condition, that is a ux at 0 comma t equals 0 for all times t. So this is the mathematical version of the semi-infinite string problem with the free end. Friends, in this video lecture, our aim will be to derive the solution for this initial value problem. And the steps will be that first of all, we will be considering this wave equation, and we will be converting this wave equation into its canonical form, because canonical forms are easy to integrate. And after converting it into its canonical form, we will integrate it to form its general solution. And after forming the general solution, we will be introducing these three initial conditions to form the solution for this Cauchy problem. Now, friends, the first two steps, that is the step of converting this wave equation into its canonical form and then finding the general solution of the canonical form, we will be writing these two steps directly in this video lecture, because these steps are exactly same as done for Cauchy problem on infinite string and the Cauchy problem for semi-infinite string with a fixed end. So on our video lectures on these two problems, we have explained this first step and this second step in detail. So if required, you may visit our video lectures on these two problems if you want detailed explanations regarding this first step and second step. These steps are exactly same for this problem also, so we are not writing them again. You can easily see these steps on those video lectures. Here in this video lecture, we will be explaining this a third step of applying the initial conditions in detail, as this will be different, as we have a different condition, which is this free end condition. So now let's begin with the first step. So friends, this is our Cauchy problem, and first step is to convert this PDE into its canonical form. And the canonical form of this wave equation is u partial derivative xi eta equals 0, where xi equals x minus ct and eta equals x plus ct are the two characteristic curves that are obtained while converting a PDE into its canonical form. Now this canonical form, you can see, is a very simple form which can be easily integrated. So our next step will be to integrate this canonical form and obtain the general solution. So we integrate u xi eta equals 0. So after integrating it with respect to xi, while keeping eta as a constant, and then integrating with respect to eta while keeping xi as a constant. So after integrating this with respect to xi and eta while keeping the other variable constant, we get this expression u xi eta is equals phi of eta plus psi of xi. So friends, this is the general solution for the wave equation, where this phi and psi, they are arbitrary functions. Next, we will be transforming this expression into its original variables, that is x and t. For this, we just have to put the values of this eta and this xi. And after introducing these values, we get the general solution of the wave equation as u of xt equals phi of x plus ct plus psi of x minus ct. And since this is the general solution for the wave equation utt minus c square uxx equals 0, so this phi and psi should be twice differentiable, as we need second order partial derivatives to satisfy that wave equation. So friends, we have obtained the general solution for the wave equation. For the detailed steps, you may visit our previous video lectures on the infinite string problem and semi-infinite string problem with a fixed end. Now next, we will be introducing the initial conditions given to us. So friends, this was the general solution, and now let's revisit our initial conditions. This first one was for initial displacement, then this is the initial velocity, and lastly this is the free end condition. Now friends, in this wave equation we have that my x is positive, my c is positive, as c is the velocity of the wave, and t is also positive. All this three implies that x plus ct will be always positive. The cases for x equals 0 and t equals 0 are discussed in these conditions. So here we have that x plus ct will be always positive as x, c and t are positive. Now when we consider x minus ct, now regarding this we are not sure. This may be positive or negative. So on this basis, whether x minus ct is positive or negative, we will be dividing our proof into two parts. This will be the first case in which x minus ct is positive. Now friends, what is my aim? I have to put these initial conditions in this general solution and get the value of this phi and psi in terms of f and g. I have to replace this with f and g, as f and g are my known functions and these phi and psi, they are arbitrary functions. So friends, first of all I will be trying to obtain the value of function phi in terms of f and g, and I will be converting phi of x plus ct into f of x plus ct and g of x plus ct. Now friends, just see the domain of f and g. The domain of f is non-negative real numbers and the domain of g is also non-negative real numbers. So both f and g, they will be defined at x plus ct, as my x plus ct is always positive. So this transformation I can easily make, and I'll be using this first initial displacement condition and the second initial velocity condition for converting phi of x plus ct into f of x plus ct and g of x plus ct. Afterwards, I'll be considering psi of x minus ct. Now friends, in this case, since x minus ct is positive, so I'll be using this first and second condition to convert phi of x minus ct into f of x minus ct and g of x minus ct. Again, since x minus ct is positive and f and g, they are defined on non-negative real numbers, so f of x minus ct and g of x minus ct will be well defined. So in this way I will be able to convert psi of x minus ct into f of x minus ct and g of x minus ct. So first case will be done easily using these two conditions of initial displacement and initial velocity. And afterwards we will come to our case 2. Now in this case 2, we first of all again we will try to convert phi of x plus ct into f of x plus ct and g of x plus ct, and that will be done using first two conditions again, and as f and g, they are defined on non-negative domain and x plus ct being positive, this transformation will be done easily using these two conditions of initial displacement and initial velocity. But when we come upon converting psi of x minus ct into f of x minus ct and g of x minus ct, this conversion will create some problem, since x minus ct is given to be negative and f and g, they are defined on non-negative domain. So I won't be able to convert a psi of x minus ct into f of x minus ct and g of x minus ct as I was doing previously. So just for this case, I need to apply some new approach, and that will be done using this free end condition. So friends, this free end condition, that is u x at 0 comma t equals 0 for all time t, this free end condition will be exploited only for finding the value of psi of x minus ct in this second case, when x minus ct is negative. For all other parts, that is calculating phi of x plus ct in first and second case, as well as psi of x minus ct in the first case, will be just using the first two conditions, that is initial displacement and initial velocity. Now friends, the proof will be going similar to the problem of a semi-infinite string with fixed end. The change will be only when we come to the second part for converting psi of x minus ct. As for this, we will be using this free end condition. So now friends, let's begin with the proof. First of all, we will be doing the steps which are common to both the cases, and afterwards we will be split our proof into two cases. So friends, First of all, let's make use of this initial displacement condition. So we introduce this initial displacement in the general solution. So this is the general solution. We take time t equals 0. So we have u at x0 equals phi x plus psi x. And from this initial displacement, we know that u at x comma 0 equals fx. So we put fx in place of u at x comma 0. And we get this expression f of x equals phi x plus psi x. So this is the expression obtained while making use of the initial displacement condition. Next, we will be making use of the initial velocity condition. So friends, this is the general solution. Now, for introducing the initial velocity condition, we differentiate it partially with respect to t, and as a result, we obtain this expression. Next, we take time t equals 0, and we remember that the initial velocity condition is that u partial derivative t at x comma 0 equals g of x. So we introduce g of x in this expression, and we get this relation between g and phi dash and psi dash. Now friends, as you must be remembering, my previous equation was phi x plus psi x equals f of x. Now here I will try to get an expression in the form of phi x minus psi x equals some expression containing g. And then I will be using these two equations to get the values of phi and psi in terms of f and g. Now for that, I need to integrate this equation to get rid of the derivative. So I interchange the sides and then I divide it by c, both the sides, as c is a positive number being the velocity of the wave. Next I integrate both the sides from 0 to x. So upon integrating I get this expression. Here I have just taken this dummy variable to be tau and then integrated with respect to d tau. And as g is defined on non-negative real numbers, so I am integrating it from 0 to x. So this integration is well defined as g is defined on non-negative real numbers. So next we just need to simply integrate this expression. Let's carry on this expression on the next page. Here, this was the expression on the previous page. Now we simply integrate this. After integrating, we'll be getting phi of tau minus psi of tau with limits of integration from 0 to x. And this expression will be keeping as it is. So upon integrating it, we get this expression. We have introduced the limits, so this becomes phi of x minus psi of x minus phi of 0 minus psi of 0, and this expression is as it is. Next, we will be denoting this expression phi of 0 minus psi of 0 with the k. So we have this expression. Next, take k on the other side, we get this expression. And here, what is my k? K is phi of 0 minus psi of 0. And since this phi and psi, they are arbitrary functions, so this k will be an arbitrary constant. Now friends, just remember this value of k as phi of 0 minus psi of 0, as we'll be needing this value afterwards. So friends, we have obtained two expressions using the condition for initial displacement and initial velocity. Now we will be dividing our proof into two cases. So friends, first case is when x is more than ct. So this implies that x minus ct is positive. As I have explained in that small outline of the proof that when x minus ct is positive, then we will be exploiting just the first two conditions of initial displacement and initial velocity to find the values of phi and psi in terms of f and g. So let's consider those equations that we obtained using initial displacement and initial velocity. So we solve phi and psi from these two equations. This first equation we obtained from initial displacement condition, and this second condition we obtained from initial velocity condition. Now we just have to add and subtract to get the values of phi and psi. So first of all, we add previous two equations to obtain the expression as 2 phi x equals fx plus 1 upon c into this integration term plus k. And then we divide it by 2 to get the expression for phi as fx upon 2 plus 1 upon 2c into this integration term plus k by 2. So friends, we have obtained the value of phi of x Next, we obtain the value of psi of x, and that will be done by subtracting these two equations. So upon subtracting previous two equations, we get a 2 psi of x equals fx minus 1 upon c into this integration term minus k. Next, we divide it by 2 to get the final expression of psi of x to be fx by 2 minus 1 upon 2c into this integration term minus k by 2. So friends, after obtaining the value of a phi and psi, the next step is to introduce these values in the general solution to get our final solution. So next step is to introduce the values of phi and psi in the general solution. Now this was the general solution you must be remembering. Now we will be just putting the value of phi that we obtained on the previous page and psi that we obtained over here. Upon introducing these values, we get this expression. In this expression, this is the value of phi and this is the value of psi. Now friends, very simple steps of cancellation and clubbing of the terms are left for this case. So here we will be cancelling this k by 2 with this minus k by 2. Next we will be clubbing this integral with this integral over here. For clubbing this integral and this integral, we will be just making use of the fact that x minus ct is always less than x plus ct. So integration from 0 to x plus ct, this can be written as integration from 0 to x minus ct plus integration from x minus ct to x plus ct. And when we write this in these two forms, then this integral with the limits from 0 to x minus ct will get cancelled with this integral, as this also has limit from 0 to x minus ct, and then only this integral will be left with limits from x minus ct to x plus ct. So upon doing these steps, we get this expression. So we have this integral from x minus ct to x plus ct obtained by clubbing this integral and this integral. And this term is as it is over here, as well as this term is as it is over here. So friends, this is the final solution of our Cauchy problem for the case x is more than ct. So friends, the solution of the initial value problem for the case x is more than ct becomes of this type: u at xt equals half into f of x plus ct plus f of x minus ct plus 1 upon 2c into integration of a g of tau with respect to d tau from x minus ct to x plus ct. Now friends, this is exactly the same as the solution we obtained for the infinite string problem, as well as for the semi-infinite string with the fixed end case 1. So the solution for the case 1 is same for a semi-infinite string with fixed end, as well as for this problem, that is a semi-infinite string with free end. Now there will be difference in case 2 as the condition is different. So now let's visit the case 2. So in case 2 we have that x is less than ct, which implies that x minus ct is a negative. So what problem this will be causing is that the domain of f and g is non-negative real numbers. So when f of x minus ct and g of x minus ct comes into picture, that creates a problem, as f and g, they are not defined on negative real numbers. So we have to follow a slightly different approach, and that will be using the free end condition. Let's revisit first of all the initial conditions given to us as well as the general solution. So friends, this was the general solution, and the initial conditions were this. This is the initial velocity condition and this is the free end condition. So friends, this x plus ct was always a positive number. So this 5x plus ct will be converted into f of x plus ct and g of x plus ct in exactly the same way as we did for the case 1. Now since x minus ct is a negative, so the same approach cannot be used for converting psi of x minus ct into f and g. We cannot use the same technique for converting psi of x minus ct into f and g, As you can see that the domain of fng, this is including non-negative real numbers only, and x minus ct is negative, so fng won't be defined at x minus ct. So for this case, we'll be using this free end condition. As you must have guessed that this condition is unused till now. This will be used only for getting the value of this psi of x minus ct. So friends, in this case, we are facing the condition that the interval x minus ct to x plus ct is extending onto the negative x-axis, where f and g, they are not prescribed. So this being the reason that we have to follow slightly different approach. So friends, let's first of all obtain the value of phi, which will be exactly the same way as we obtained in the previous case. So friends, this was the general solution, and now first of all I will be getting the value of phi, and for getting the value of phi I consider the equations I obtained previously. This equation I obtained from the initial condition of initial displacement, and this equation I obtained from the condition of initial velocity. Now I add these two equations to get the value of phi as follows. Phi of x equals fx by 2 plus 1 upon 2c into this integral plus k by 2. So friends, for this general solution, I have obtained the value of phi. Next I am left with the value of psi. Here friends, this was the general solution, and this is the value of phi that I have got, and I will be putting over here. Next, I still need the value of psi of x minus ct. And in order to get this value of psi of x minus ct, I will be exploiting the free end condition. And the free end condition is given by this expression, that is u partial derivative of x at 0 comma t equals 0. So friends, this is the general solution. And now in order to use the free end condition, I differentiate it partially with respect to x. So I get a u partial derivative of x at x comma t is equal to phi dash x plus ct plus phi dash x minus ct. This expression I obtained upon differentiating this expression partially with respect to x. Next I take x to be 0 and I get this expression. Since I know that my free end condition was that ux at 0 comma t equals 0, so I have put this 0 instead of this ux at 0 comma t. So this is the expression I have got after making use of the free end condition. Now friends, the aim of using this condition is to get the value of a psi of x minus ct. So somehow I need to get this psi into picture. So for that I need to integrate this term so that I can get rid of this derivative and get psi function. So I will be integrating this expression, and I will be denoting this term c into t with the tau. Now this c is constant as it represents the velocity of wave, and this time t, this is a non-negative number. So this tau is a variable varying from 0 to infinity, as a t varies from 0 to infinity. So next step is that I am replacing c into t by tau, where tau is equal ct, which is non-negative. So now next I will be integrating with respect to tau with limits from 0 to ct. Here, after integrating it from limits 0 to ct, I get this expression. Now after integrating this term, I will be getting phi of tau minus psi of tau with the limits from 0 to ct. And then I will be introducing the limits. And this side will vanish as this is integration of 0. So upon putting the limits of integration, we get this expression phi of ct minus psi of minus ct, since we have a minus tau over here, minus phi of 0 minus psi of 0, as integration was from 0 to ct. So we get this expression. Now friends, in our previous pages we had obtained a condition that was k equals phi of 0 minus psi of 0. This condition we obtained when we were exploiting the condition of initial velocity. There we obtained this relation. Now we'll be using this relation over here. We'll be denoting this phi of 0 minus psi of 0 by k. So upon denoting it by k, we get this expression where this value of k as phi of 0 minus psi of 0, we are using it from equation number 5. If you visit the equation number 5, you will see that there we denoted phi of 0 minus psi of 0 with k. So now let's take k on the other side, and then we get the value of psi of minus ct equals phi of ct minus k. So friends, we have got value of psi on negative numbers. As c is positive and t is non-negative, so c into t will be non-negative, and so minus c into t will be non-positive. So we have obtained the value of psi on non-positive real numbers. Now let's carry on this expression on the next page. Here, this was the expression we obtained on the previous page, that is psi of minus ct equals phi of ct minus k. And this c is positive, t is non-negative. So c into t is non-negative, and minus c into t will become non-positive. So we have got the value of psi on negative real numbers also. So now we write this expression as this: psi of minus alpha equals phi of alpha minus k, where this alpha is a non-negative. Since we are replacing ct with alpha and ct was a non-negative. Now we can write this also in this form, that psi of beta equals phi of minus beta minus k, where beta is less than equal to 0. And now as x minus ct is negative, so we can obtain the value of x minus ct using this relation, as beta is non-negative and psi of beta is defined in this way, 5 minus beta minus k. So psi of x minus ct equals phi of minus x minus ct minus k. So phi of minus x minus ct becomes phi of ct minus x, and this is for the case x is less than ct. Now as ct minus x is positive, so phi of ct minus x at this value we can write from the expression for phi that we obtained previously. So now we have just put the value of phi of ct minus x over here. This is obtained by the value of phi that we obtained on the previous pages. So on using that value of phi over here, we get that psi of x minus ct, which was phi of ct minus x minus k, becomes half into f of ct minus x plus 1 upon 2c into this integral plus k by 2 minus k. This minus k is kept as it is over here. Next will be just clubbing this k by 2 with this minus k. So friends, upon clubbing those two terms, we get this as the expression for psi of x minus ct, which equals a half f of ct minus x plus 1 upon 2c into integral of g tau with respect to d tau from 0 to ct minus x minus k by 2 for the case x is less than ct. So friends, after exploiting the free end condition of ux at 0 comma t equals 0, we obtained this expression. And then in this we just replaced c into t by alpha, so we got this expression. And afterwards we just wrote it in this form, that psi of beta equals phi of minus beta minus k for beta to be non-negative. And hence we could write the value of psi of x minus ct equals phi of ct minus x minus k, as x minus ct was negative. So I could replace this beta with x minus ct, and phi was defined on non-negative numbers, so phi of ct minus x will be defined. And then just upon introducing the value of phi that we obtained on the previous pages, we got this expression, and clubbing these two terms we finally got the value of psi of x minus ct for the case x is less than ct. So friends, upon getting this value, now Only one last thing is left, that is to introduce the values of phi and psi in the general solution. So for that, let's revisit our general solution. So for the case x minus ct, I will introduce the value of phi and psi. In this general solution, u at x comma t equals phi of x plus ct plus psi of x minus ct. Now, the value of phi that we obtained on the previous pages was this, and the value of a psi of x minus ct that we just obtained previously is this one. Now next is to club these two terms. Now you can see that this k by 2 will get cancelled with this minus k by 2 over here. And upon doing that, we get this expression. Now we'll be just writing it in slightly standard form to get this expression. So u at x comma t equals this expression is the solution for the case x is less than ct. For getting the solution, we just put the values of phi and psi we obtained on the previous pages, and upon cancelling k by 2 with minus k by 2, we received this expression, and then we just took 1 upon 2c common to get this expression. So now this is my final solution for the case x is less than ct. The solution is that u at x comma t equals a half into f of x plus ct plus f of ct minus x plus 1 upon 2c into integration of g tau with respect to d tau from 0 to x plus ct plus integration of g tau with respect to d tau from 0 to ct minus x. So this is my final solution for this case. So friends, this expression you can see is different from the expression we obtained for the semi-infinite string with fixed end condition. There we had just one integral, and here we have two integrals. Now let's write the two cases together. Here, for the case x is more than ct, we had uxt is given by this expression. For the case x is less than ct, we obtained that the expression for u at x comma t is this one. Now you can see between cases 1 and 2 there is a difference. One difference is that x minus ct in this expression has been replaced by ct minus x, and then the integrals are split into two integrals. So the free end condition results in these two integrals and ct minus x instead of x minus ct. So the solution of a semi-infinite length string with the free end in the clubbed format can be written in this form: u of x comma t equals this expression for the case x is more than ct, and equals this expression for the case x is less than ct. So friends, do remember the difference in the terms in the two cases, as this will be very important when we come to solving a question based on this problem of a semi-infinite length string with free end. So friends, do also remember the difference between solution for this problem of free end and the other problem of a fixed end. The two solutions are different, and the difference lies in this case when x is less than ct. For this first case, x more than ct, the solution is same for this free end as well as for that fixed end condition that we dealt in the previous video lecture. But for this case 2, the solution changes. So do remember those changes. So friends, now we come to the end of today's video lecture. In this video lecture, we have derived the solution for the semi-infinite string with a free end. Hope you liked our lecture. Do visit our site lilearn.com and also provide us your valuable suggestions and feedbacks to us. Thank you.